there are people in my time when I started my career in the 1970s, the workmen and supervisors used to say that when I am there, everything goes on well. When I am not there, things don't seem to be all right. And we used to be very proud of such kind of people and saw to that they never left the organization. In fact, one fellow used to put a gunny bag screen. Then over a period of time, people have started understanding that there is a lot of science behind it. And then a formal appreciation of how do you get a casting? How do you enter the metal inside? And what do you do when there's a shrinkage? And how do you feed them? I've said it in very simple two words: the gating and feeding of castings, part one and part two. But the very definition itself can go for pages. So let us see how do we go about. Now, what you see here is a casting filled, about to be filled, in a fraction of a second, I would say. A picture was taken, and this is what it looks. Now, this is actually a simulation from one of the simulation software, maybe Magma software in this particular case. And why I'm showing this is nothing looks ordinary here. Everything is messy. You see a lot of particles here. You see turbulence when turbulence was not expected. And somebody said the last gate should be more effective than the first gate. Actually, you will see that here. And there are so many aspects which conform to theory and many which do not conform to theory. And this is what exactly. This particular casting is not a showpiece, it's a reality. I personally would have poured thousands of these castings and earned good lot of money for the organization. But we made one mistake. I said when it was success, when there was a mistake, I said we. No, I made a mistake. And we lost several thousands of castings and bringing the company almost into a big loss. We could avoid it in time and move forward, all because a small change was done in the gating system, which introduced turbulence in one place, and in other place there was a cold shut, and eventually we lost a lot of castings. So this is just to show the sort of significance of the liquid metal which is in the mold cavity. I'm not really going to show you many of the simulation studies which you foundrymen would have seen day in and day out. And the minute you close this webinar, probably you will go to the laptop and see some of the simulations here. So I'm not showing that, but let's see the principles of how this works. You would have heard about John Campbell. John Campbell is a contemporary living foundryman, an Englishman. I think he's in the United States now. In fact, his book, The Castings, is one of the most celebrated books in Foundry, if you ask me. And we invited him to India about 10 years back for the International Foundry Congress. I remember Sham Arjun Wadkar got the best paper award for that. Did you, Sham, on that occasion? Yes, he must have got the best award paper. Anyway, what I'm saying is John Campbell came to India, and so he's not a nobody. It says, when the molten metal enters the mold reacts violently. Frenzied activity crowds into this brief moment of the birth of the casting. John Campbell, an Englishman, so his English is also beautiful and brilliant, in addition to his knowledge in foundry. The buckling and outgassing, pressurization, cracking, explosions, disintegration, and chemical attack are examined only by finest understanding of physics, chemistry, metallurgy, material science, and not by experience alone, though that's invaluable. The survival of the casting is only ensured by the strenuous efforts of the casting engineer. Now, why I say this is, it's very customary for many foundrymen, even today, to say that casting is an art, and why should I worry about what I read in school, physics, chemistry, metallurgy, material science? In fact, people are very proud in saying, especially if they've made a success in life, that I don't remember what I studied in school. I am not talking about college or higher education or research. I'm not interested. It doesn't help me. I read it for exam, I passed. And believe me, like many of you here, I have shared my time and experience with quite a lot of foundrymen in the country and in the world. Thousands, I would think. It is not special to India. It's special in many other places in the world that people say, "Oh, theory, put it down. We are not interested in theory. It works. Nothing equals experience." Now, the point I wish to say is that all the breakthroughs in technology and science have come from theory only. Obviously, theory appears very sort of outdated, and it's not easily reachable by everybody. And many of the people who started the theory themselves have not made well in engineering or in advanced manufacturing, but the theory stands. Like what Newton did, or what Einstein did, or what Heisenberg did, they themselves may not have realized what they did, but over a period of time it stood. So what I'm trying to say, gentlemen, especially the younger generation, is go back and read your physics, chemistry, metallurgy you might not have read, material science you might not have read, maths. These three go invariable in taking you to the higher heights in Foundry. Okay? And don't think experience alone will make a good foundryman. I know a lot of people are sitting in the audience who may not agree with me with experience now. If you're not able to explain to people in clear words why you got it correctly, then it means we have not understood the process correct. Werner Heisenberg, the celebrated physicist, is known to have said on his deathbed, okay, if I encounter God, I'm going to ask him two questions. Okay, why relativity and why turbulence? Heisenberg, I think many of you would have known, he spent a lot of time in India and Himalayas, one of the greatest physics minds in the modern world. People say that he's next only to Einstein, he and Niels Bohr. So he's going to ask God, I believe, why turbulence and why relativity? Okay. And he says, God will have answer at least for one question, which is on relativity and not on turbulent flow. So it is something which we have not really understood turbulence very well, though we have seen ourselves as turbulence in many facets of life. According to Richard Feynman, fluid flow in open channels is one of the least understood branches of physics. And gentlemen, we are dealing with this day in and out. Fluid flow in open channels, because when you pour a metal into a mold cavity through the pouring basin and downsprue, till the mold is filled, it's open flow. Okay. Now, you have to stop for a minute and contemplate why I said this. Take a glass of water or milk, spill it over a table, which you would have done inadvertently many times, but you do it deliberately this time. Then try to repeat the same pattern next time. It's not possible. I don't think any physicist in the world would have clearly understood what exactly happens when you spill a little bit of water or a milk on a table and how it spreads and whether you can repeat it, let alone understand it properly. Okay. So that is what we are dealing with day in and day out. Now, I'm not going to spend much time on practice because a huge field. And when I see some 100 participants here, at least multiplied by 20, 100 into 20, 2,000 years of foundry experiences behind this audience. And we're all extremely capable and very good. So, but I'm going to spend a little time on the theory of casting simulation. We'll talk about fluid dynamics first, and then we'll talk about heat transfer. Though both are going to be covered on different days, just as a covering, what you call a screen, we can go through both. Fluid dynamics and statics are controlled by an equation. I'm not going to scare you, gentlemen, don't worry. I am not going to put any equation in my presentation, but the word Navier-Stokes equation, which simply says when you throw a fluid, compressible or a non-compressible fluid, when it moves about, what laws govern that? Okay, conservation of energy and conservation of momentum. These are beautifully brought up by the Navier-Stokes equation. If any one of you happen to read the book Anderson, which is on computational fluid dynamics, he starts with this and goes. one of the most beautiful equations. Now, fluid dynamics and statics, whatever the simulation software does, whether you take Magma or whether you take Flow 3D or whether you take any other simulation, it's based on Navier-Stokes equation. Now, how exactly they have absorbed this in the computer, not because they don't know, because of the limitations and understanding, bringing the what you call uh, the non-linear differential equations to a computation presents an extremely difficult thing. How much they brought it to the computer is another thing. For example, I'll tell you, very simple thing. You drop a stone, it reaches Earth from a height. We assume gravitational field G and S is equal to half gt square. But we all know, we studied in school physics, G is not constant. It keeps changing as the stone reaches the surface of the Earth. Okay. So how do you assume a constant G? No, you have to assume a variable G. The equation straight away becomes a non-linear in the sense the height which you are calculating depends on the gravitation. And the gravitation itself depends on the h. This is called a nonlinear equation. And you drill a hole into the earth to reach the center of the earth. When it goes down, again the gravitation increases because it's near to the center of the earth. But mass decreases because it's only that mass which is covered under the radius is to be calculated. It becomes extremely complicated. Now, all our equations in fluid mechanics or heat transfer, they're all nonlinear differential equations. Now, we have struggled a lot in the first half of our life till we reached the age of, we started working in Foundry age of 2022. Almost for 20 years, we didn't have good simulation packages at that point. And we had, okay, the Fosico had one. And that was more of, they themselves said it was not very accurate. Some simple. But then later, great companies they were all promoted by Aachen University in Germany and in NASA in America. A lot of theory came into fluid flow and thermodynamics. And these non-differential equations were tried to be solved, not solved, to be digitized. Okay. And then things happen. But believe it or not, gentlemen, when you pour a metal, okay, or when tsunami takes place, Navier-Stokes equation works there. Now, we are all very simple foundrymen. Why should we worry about all this? Now, somebody gives this in a beautiful form of simulation, have it and forget about it. Now, do you think this is the approach we take? Fine. I would think if out of 100 foundrymen, 99 take this view, no harm. But I think 1 in 100 should know that what is behind this Navier-Stokes equation? What is behind the simulation software, which I paid about 1.5 crores of rupees and bought? Is it correct? Or somebody is taking me down the garden path by giving very simple, what you call thumb rules instead of giving a beautiful simulation based on mathematics. So this is why I wanted to mention about this equation, one word Navier-Stokes equation. We spent at least about 5 minutes. At least 1 in 100 foundrymen should go deep into that and find out what the hell is this Navier-Stokes equation. Let us go down into that. Next one is very familiar, Bernoulli's theorem. Okay. For those who are not initiated to Bernoulli's theorem, I will say that it's a conservation of energy. If you drop a stone, before you drop, it had a potential energy which depended on the height. When you drop it, it comes with a big velocity, so that is converted into velocity energy. If it's a closed channel, the pressure also changes. So Bernoulli's equation theorem simply says that the sum of potential energy, then the kinetic energy and the pressure energy is a constant. H plus V square by 2G plus P by W is a constant. That's what it says. Fair enough. Simple. Law of continuity. What is law of continuity? You take a pipe, suddenly increase the diameter, okay? Or let's say reduce the diameter as you would have done by forcing water into the plants in the garden, the velocity comes with certain speed when the diameter is bigger. When the diameter becomes smaller, the velocity increases. So the area into the velocity at any point of time is constant, which is simple. Otherwise, where else the water or the liquid metal can go? No, you can't compress it. Okay. The law of continuity doesn't work in compressible fluids. Okay? It works only in non-compressible fluids. Flow in open channels is one of the least understood branches, I said. It is not beautifully handled even by the most modern simulation software. Turbulence, to some extent, turbulence is being handled. As we go through, we'll try to find out how turbulence is handled in the simulation software and what is it. Suppose you don't have simulation software, what do? You'll handle all that. Heat transfer, I'll just run through very fast because next week, Monday, we are going to do that. Conduction, convection, radiation. Radiation is not covered in any of the simulation software. The basic principles of Archimedes' principle, it is not on heat transfer. I think I put the heading differently. Okay, things float, how they float is, floating is not Archimedes' principle. Archimedes' principle is the volume or the weight of the liquid which is displaced is equal to the loss of the weight. We'll come to that later. A good lot of metallurgy goes in the theory of simulation. Sievert's law of partial pressures. When you melt copper-based alloys, it takes in a lot of gases, oxygen and hydrogen. How does it take? What are the principles which goes in Sievert's law of partial pressures tells you? Why water boils? I would recommend, gentlemen, that people who are initiated and inclined to some theoretical work, buy the 3 volumes of physics by Richard Feynman, a chap who died very recently, a Nobel laureate, considered one of the greatest minds in Berkeley. Buy his books. I hold it. Even today, when I have any doubt on any of this, I buy. In a beautiful way, he explains what is boiling, what is Sievert's law of partial pressures. Okay. If anyone of you want to elaborate on this, we'll go through. If there is time, we'll go through. Otherwise, I will expect you to be in chat with me. You have my number. You can do that. Lattice structure. When liquids solidify, they form the lattice structure. And how they change over a period of temperature is lattice structure. Free energy and entropy. Okay. Equilibrium diagrams, phase transformation. These are all the theory of casting simulation, or simulation. I should not have used the word, the theory which goes behind the simple casting which you see, the manifold or the engine block, whatever you see in front of you in the shop floor, are a beautiful artifact. I bought a beautiful Krishna statue the other day, one of the most beautiful pieces. What goes behind is some liquid metal has gone into this, okay, and eventually it has produced a casting. Gentlemen, don't think I am theoretical. 100 years back, people did not understand gastroenterology. They had something else came out, and there was some energy somewhere in the body, and they had to move around. That is one way of looking at it. Over a period of time, the anatomy people and physiology people understood what happens in the body, what is an alimentary canal, or in the case of renal system, what happens when you drink water, it goes down, and what absorption takes place. When the theory improved, I think a lot of understanding improved, and the general life expectancy of people improved. I'm not talking about the present case of, let's say, the viral infection, where all, the fear which are going through in the world. But generally, what happens inside, there are 2 ways of looking at it. You don't have to worry about it. You don't have to worry. Why bother? My grandmother never bothered. She lived for a very long life. Another is try to understand what happens. The human nature is to keep on trying to probe what happens, why it's happening. Not what happens, why it happens. And I explore it further. Okay. Right. Now, history of casting simulation. Experimental simulation of fluid flow. What happened? They found out there are some numbers, okay, which were identical. Some of the fluidity numbers were identical to water. So University of Birmingham did some work on water models. You put water in a what you call a transparent vessel, Make an opening in the bottom or side, whatever you want, how it flows, have a gating system, simulate the gating system of the casting, okay, in polystyrene sheets, make a box out of it, and then try to find out how the whole thing works. And Professor Kondik, a well-known figure, he is the professor of many of the professors whom I know. And in my time, Kondik's paper was referred invariably in many of the references. My own Professor Mandyam Srinivasan, late Mandyam Srinivasan, it's unfortunate, he passed away a few months back. He worked under Kondik, and he used to show us what are the work they did in Birmingham and how the water actually flows and how they expected liquid metal to flow in the similar way. So that was the experimental simulation of fluid flow. Mathematical work on simulation was on the fluid flow. I already told you before, the what you call in the previous slide, we had the Navier-Stokes equation, the Bernoulli's theorem, lot of continuity. In the case of heat transfer, the earliest books were Karstler and Jaeger. Semi-mathematical, Shorinov, finite element difference analysis. It didn't come to fluid flow in the early days. It came only for solidification of metal. One of the earliest works was done in the Institute of Science. Professor A. Ramachandran, who later became director of IIT Chennai, he was our professor who started teaching us. Then Professor Krishna Prasad, who later went to Indore University, I was one of his students, and a very initial work was done on trying to solve the conduction heat transfer, which is a very nonlinear equation, by mathematical means, trying to find out, integrate, differentiate, do this, do that, and find out very simple formula like S is equal to half GT square, something like that we wanted to find out. Oh, the answer was almost no. So we could find answers for semi-infinite modes, which had no sort of relevance at all in the foundry industry. For example, if you take a glass of water or milk and keep it in the freezer, believe it or not, gentlemen, there is no absolute mathematics to tell you how long it is going to take for the water to become ice. No, there's no absolute maths. It can only tell you this approximate. So we went through what is called as approximate methods, variational calculus method, and we tried to do something. I went to the HL computer and did some simulation in computers and got the prints. Those days we have to write the software ourselves and do the punching, not punching of card, punching of tapes ourselves, and do all that. Much later, in the Castings Technology International, which is formerly called as a BCI and as CRATA, where I was a council member, we did a comparative study of simulation software, comparative study. Almost about 30 software available. It was almost about maybe 10 years back. Almost 30 simulation software available at that point. Compared all of them to try to find out which was more accurate or which was giving identical figures and which was, what was the final conclusion? It was a very educated and a very highly sort of focused study done by a very able person in the Castings Technology International. And finally, they found out when you talk about the freezing of casting, solidification, there's not much of a difference between one and the other. But in the case of fluid flow, hell of a lot of difference between one and the other. And I'm not trying to propagate here. A few software like Flow 3D were able to handle even compressible fluids because Flow 3D originated from NASA, National Aeronautics and Space Administration. Those guys understood even compressible fluids because it's gas turbines. So they were able to handle this and they adopted. And later, there's no great intellectual property right barriers in those days. And many people could take it. I won't say copy it, adopted it and modified it and did that different. But it's approximate. Now, I asked, very eminent people, Conrad Weiss from Aachen University, why so? He said, Gnanamurthy, the maths is very predictable, at least in conduction heat transfer. Though you are finding it very difficult to solve it as an absolute mathematics problem, but we know the equation. But in the case of fluid flow, it is not there. even the what you call Navier-Stokes equation doesn't handle the fluid flow completely. So that's why we are at this stage. What I am saying is, we are talking about fluid flow. We are talking about uh, what you call solidification on 2 lectures. Fluid flow, even the modern methods, whatever you see, the beautifully presented simulation, what you see, I'm going to show you some here, even the beautifully simulated ones are approximations. One never knows whether that exactly happens. At least in the case of conduction transfer, or let's say the solidification, the simulation predicts certain defects in the casting. Okay, predicts. So you can cut a casting and try to find out whether the actual shrinkages, whatever you see in that casting or in the riser, is same as what was predicted in the simulation software. That option is available to you here in the fluid flow. It is not available. Only by second and third hand methods you have to see. There was a turbulence and there was a sand erosion, there was a oxide formation, like what John Campbell says, a double oxide layer, and that is formed in the casting. And all this must have happened because the fluid flow was not good. You know, legally, if any one of you read John Grisham or any of the legal books, you know, second-hand information can never be allowed as a witness, even in legal systems. You know, it's only what is perceivable very clearly. And in fluid flow, it is not there. So you are dealing with such a, what you call, dichotomy in fluid flow. So before we go further on fluid flow, so what I need to tell you here is, if you give the problem to simulation software on a fluid flow, it doesn't tell you anything at all. It just blinks at you. You have to tell it, of course, it will tell you what's the total weight of the casting plus the gating system, which are very approximately gust. It will tell you what it is. Then it asks you what is the filling time. Now you give a gating system, it doesn't tell you what is the filling time. It doesn't. So even today, with the most modern simulation software we have to do a lot of paper pencil work ourselves and feed it to the computer. We had a lot of debate on one of the what you call chat groups in WhatsApp, where a lot of internationally very well-known people were there from many parts of the world, like East Europe, England, formerly CDC people and all that. This is what we all felt, that, yes, you need to tell what it has to do, and then it will tell you whether it looks nice or not. Then you give one more set of data, it will again calculate and find out whether the first one is better or the second one is better. That's what it does. So first one and second one, gentlemen, we need to do ourselves. Very fundamental. For the benefit of the further slides, I'm going to show this. Pouring cup, sprue, down gate. The runner, cross gate you can call, and 3 gates are there at the casting. Okay. Now here he has given the gates on the top of the runner, and the gates are attached to the bottom of the casting. You don't ask me whether this is the right way or the other one is right way. This is an example. John Campbell somehow thinks that this is not correct, and the gate should be in the bottom. We'll not get into discussion on that. Okay, we will just say that this is what it defines. Not that you don't know. Such of those who are into students or very academic, who are not gone into the foundry much, this is what it is. Okay, right. Now, what is the empirical calculation for gating system? Now, the pouring time is dictated by 2 factors. One is the minimum wall thickness of the casting. Okay. You may have a 1-ton casting with a 1-inch wall thickness, or you may have, let us say, a 100 kilo casting with 1-inch wall thickness. In both the cases, the wall thickness is the one which decides on one aspect of the pouring time. Okay. And another one is the total quantity of the liquid material itself you take. There are 2 components to the formula. Let me see whether I have the formula here. Yes, we have the formula. Okay. We'll come to that later. What are the things which you require? Pouring time is dictated by minimum wall thickness of castings. 1 minute, hold on. Now, velocity, as you pour the liquid metal through the downscrew, it comes through and enters the runner. The velocity of that is decided by the height of the liquid metal. That's the cope height. It's very simple. Take a drum, fill it with water, make a hole in the bottom. The velocity of water in the bottom is dependent only on the head, which is what we said Bernoulli's equation. H is equal to V square by 2G in the bottom. Many of you may not immediately agree with me. Whether you make a bigger hole or a smaller hole, the velocity is same. It may find it very difficult to believe this, but it is same. If you measure the velocity by the distance to which it goes before reaching the floor, you'll find it is exactly same, but I'll warn you, you put a smaller hole, it takes a longer time for the water to deplete from the top of the drum. But when you put a bigger hole, it depletes faster. So the trajectory of water where there is a bigger hole, it shrinks much faster than the one which is in the smaller hole. So you get a feeling that as you constrict the diameter, the velocity is more. No. Well, you have one more experience. You take a hose, connect it to the tap, and try to sort of pour water into your plant or garden. Now you will find it's coming with certain speed. You try to sort of pinch the rubber tube in the end so that to make the area smaller, you will find suddenly the water coming with a bigger velocity. Now, is it not contradict to whatever I said just now? Now, I was thinking about it for a very long time. It is not so. What really happens is when you have the diameter bigger, there's an open flow somewhere, open flow. So the water is not building up. The water is not building up in the channel. And then, hence, the velocity is very low. But when you pinch it, try to sort of make it smaller, what really happens is there is a buildup and you are actually getting the height at that point of time only. And hence you get a feeling that you're getting higher velocity. But forget all that. The velocity is dependent on the height of the downspout. Now, given the above two, the minimum area for flow choke is calculated. We'll come to that. If choke is in gate, then the system is pressurized. If the choke is in sprue, then the system is unpressurized. Now, what exactly this means? You are going to a cinema theater, okay? Now, let's say there are 2-3 gates, okay? And you will see that in marriage hall, when you sort of presented and when you wish the couple you want to go for dinner, the dinner room gate will be there, one gate, then there's another gate, then there is another gate. The first gate is very small, okay? It does not allow a lot of people. The minute you cross that, you are free to move around. Then if that is also, let's say, smaller than the final gate, when you go to the final gate, you are really free to move. Now, this is called the unpressurized system. Now, the complete constraint is in the very beginning, and from then on, the metal is free to flow. Now, this is a highly open surfaced and non-filling fluid flow in open channels in unpressurized system. In pressurized system, the other way. There's a big gate, okay? Anybody can go. Then there's a smaller gate. Finally, you really enter the dining hall. There is one chap who is standing there, says, sir, wait, sir. There are only 10 seats available. You can go, and another 4 seats. Like that. Now, the complete constraint is on the other end. Okay. Now, this is called the pressurized system. Here, the gating system gets filled immediately, and from then on, it's not a open channel flow. It's a full channel flow. Okay. So this is something which the difference between the pressurized and unpressurized systems. Now, how do you actually do? I don't know. Many of you may already know this, but for want of the benefit for the majority, let me go through the whole thing. Find out the weight of the casting from solid model or drawing. In my own good old days, the solid model was not available, so we had to calculate volume, pi d square into h, lb, h, and whatnot, and then find out, multiply bed density, and try to find out what is the weight of the casting. Assume to start with 55% for a steel castings or 75 for a iron casting or whatever it is. Ductile iron maybe a little more. You assume that. Okay. From solid model drawing, find out what is the minimum thickness of the casting. What is the minimum thickness? Right. Pouring time is calculated by the following formula. Pouring time is equal to fluidity factor. There's a fluidity factor. In my time, we used to find the fluidity factor by pouring the fluidity spirals in the foundry. Liquid metal used to be taken from cupola, then pour a small spiral. Many of you may remember here, and 40 inches is the total length of that spiral. If it goes for 30, the fluidity factor is 30 by 40.75. It depends on temperature, it depends on silicon, it depends on carbon or carbon equivalent in the case of iron. So take a fluidity factor into bracket 0.95. Don't ask me how we got all this. This is a thumb rule, absolute thumb rule. For want of anything better, we are using it even today. And some computers, people say, no, we tell you what is the pouring time. Sometime back I told you, computer does not tell you the pouring time. But some people say, no, it tells you. No, it doesn't calculate by first principles of physics. It does by interpreting this type of an arithmetic behind a small within the computer. It does this calculation. And when you do it, you'll find it same. It's a 0.95, he may use 0.93, whatever it is. Minimum thickness of the casting in inches divided by 0.853. Don't ask me how, 0.853. Multiplied by square root of the weight of the poured weight of the casting in pounds. Okay. If the weight is less than 1,000 pounds, if it is more, for the third root. Okay. Now, this is how you find out what is the pouring time. Velocity is calculated by head. And what happens if the entry of the metal is not in the bottom, if it is somewhere in the middle? Now, h is the downscrew height. P is the height of the casting above the gating plane. C is the total casting height. So finally, the head is h minus pp by 2c. Okay. Now, if p is 0, that means the whole thing is not there. Then head is equal to h. That's all. It's as simple as that. Okay. Velocity is 0.8 into root of 2gh, which all of us know. But g is acceleration due to gravity, 9.81 meters per second. So we calculate the velocity in this particular way. So we know the velocity. We know what is the pouring time. Okay. Now, when you multiply these two, you will get the total quantity of the metal which is formed. Imagine for a minute, you have a pipe, water is coming out of it. Okay, what is the amount of water which has come out? The time multiplied by the area of cross section multiplied by the velocity. If the three are known, you know the total weight or volume of liquid which has come out. Or if you know the volume of the liquid metal and already calculated T and already calculated the what you call the velocity, you can find out the area which you call as the choke area. So choke area here is weight of the casting divided by density, velocity per unit. Density comes because we have been talking in terms of volume up till now. In order to bring it to weight, you put the density here. Then you decide the number of gates. Okay, whether 1, 2, 3, 4, depending on the configuration of the castings. Okay. Even today, I have seen people pouring with 2 down screws, but I don't buy that. Have 1 down screw. If it's a circular casting, find out why not you pour through the center and all that. Decide the number of gates or through the side. Decide the gating ratio. Preferably, I don't know what is it I have written here, 1:2:4, because my screen is hidden here. 1 minute, give me, gentlemen. 4, 4. Yeah, 1:2:2. People go for 1:2:4 for precise system. In unprecise system, it's reversed. The area is, what you call very large. Now, this is in the reverse order. 1:2:2 simply means 1 is the gate area, 2 is the runner, 2 is the downspool. Now you can go for the reverse, 4:2:1. So that means you have a very high, opening in the gate, then constraint and then constraint, right? Calculate the runner bar and downspool dimensions. Now give this to the computer, find out what it says. It will tell you the velocity at various points in the casting. That's what it will tell you. Okay. Because you've already given it what time it takes for filling, right? And it will tell you whether there are any turbulence at any point of time. Now I'll tell you, given the velocity, we are well equipped to calculate the turbulence ourselves. Otherwise, it also tells you. Now, just give me 1 minute. Now, almost all of you have a simulation software at the factory, or you may have access to the simulation software by some agencies. And then you give this data, then it will run and show you how the mold filling takes place. Very approximate idea, it tell you, okay? And then you find whether it is satisfactory or whether you have to do one more exercise. I'm giving you some examples of Bernoulli's theorem and law of continuity. Now, you can look into this picture, or otherwise I'll give you another example. You open a tap, okay? Water comes out of the tap in a beautiful way, what we call as a streamlined, in the first 1 second, the water drops by 16 feet. S is equal to half gt square, 16 feet. Suppose you have this tap high up on the, what you call, 3rd floor or 4th floor, and you want to see how the stream hits the floor. In the next second, the water travels by 48 feet. For 2, S is equal to 64 S of gt square. 64 minus 16 is 48 feet. So what has really happened here, gentlemen, is the 16 feet of water has become 48 feet now. Doesn't seem very comfortable in getting stretched to 48 feet. So it slowly breaks loose, like whatever we have here, it breaks loose. And then you take another 1 second, it becomes uncontrollable. If you go to any waterfalls like Kuttalam or Joke Falls, or the Niagara Falls in America or Canada, you go there, you find it becomes a mist. So what happens is, when the surface tension force is not able to hold on, it's not the viscous force, please let's not mistake this, the surface tension force is not able to withstand the inertial force in the center, it breaks away, and it becomes a 2 streams, 3 streams, thousands of streams. The minute this happens, you get into a lot of problem in foundry, like this, the center one you see. 2 things. Now, not the center one. I'll tell you what happens here. Now, yeah. So when it becomes broken down like that, now the same amount of liquid metal has got more surface area now, right? Because you take an apple, cut it into 4, you got more surface area now. That's why we break an ice and put it on a soft drink or your whiskey or whatever it is. More surface area means more absorption of gas. Gases from the outside can get in easily into the liquid metal, and in the skin itself, it can form an oxide layer. The minute an oxide layer is formed, when the liquid metal laps on itself, it doesn't fuse. So John Campbell calls it as a double layer oxide film. You got an oxide layer, you fold it, it doesn't join. You make chapati, okay, thin. You put a lot of water, powder on the top again, and then again close it. The two layers of chapati doesn't join because there is a loose wheat flour on the center. Imagine instead of the wheat flour, if it's an oxide layer, when oxide layer with that, when the liquid metal folds on itself, which happens in turbulence, then it doesn't fuse. So it is entrapped. In the case of chapati, you want it, but here in the casting, you don't want it. So the entrapment is a big problem. So that is why you don't want turbulence for two reasons: absorption of gas and double air. Now, this is another thing. Now, the second picture, whatever you have, is another. What happens is, instead of a tapered down screw, when you have a straight down screw like this here, this portion is a vacuum, low pressure. Because if you apply Bernoulli's equation also, when the velocity is high, the pressure becomes low. And hence it can take in a lot of air from the liquid metal which is above the pouring basin. It can take. So you do not want, one is, which is a trivial thing, the down screw should be tapered. The other one, what I said was the turbulence should be avoided. Now, how do you calculate the turbulence? The flow of liquids can be characterized by a special measurement called the Reynolds number, which can be calculated by Reynolds number equals velocity into density into diameter, or whatever you call, divided by the surface tension mu, the viscosity of the fluid in this case. I'm sorry, viscosity. It simply means that the numerator, well, where is my cursor? The numerator is the momentum force. You have velocity, you have density, and you have all that, isn't it? The denominator mu is the viscosity. If this breaks to 2000, if Reynolds number is less than 2000, the flow is characterized as laminar, with the molecules of the liquid tending to move in straight lines without turbulence. Okay. If it's more than 2000, it's turbulence, and you don't want that. Here, system has a Reynolds number. Between 2000 and 20,000, some mixing and turbulence will occur. This type of turbulent flow, common in most foundry gating systems, can be considered relatively harmless, though I would think we won't go up to that level. We'll try to contain it to 2000. But can be considered relatively harmless so long as the surface is not ruptured, thus avoiding air entrapment in the flowing system. With Reynolds number above 2000, flow will be severely turbulent and nobody can help you. This will lead to rupturing of the stream surface with a strong likelihood of air entrapment and dross formation as the flowing metal reacts with gases. We can have a lot of discussions on these topics. I don't know whether this webinar is meant for such kind of detail. Why you go for pressurized versus unpressurized systems, okay? And vertical and versus horizontal gating systems. Okay. Pressurized and unpressurized systems, I'll tell you what's the difference. In the pressurized system, when the liquid metal gets into the mold cavity, it's at a very high velocity. It's almost like a jet. It's waiting to get into the cinema theater. As you get in, if the room is not full, you try to go here, there, oh, that seat is better, daddy will go there, or maybe let's go here, and we move around, and then finally settle. It's exactly what happens to liquid metal in a pressurized system. Okay, it just goes there with a lot of velocity, and hence the turbulence possibility is very high within the mold cavity. Right, but in the case of what you call many gating system, this is preferred when you are not worried about the gases. Okay, it is preferred. Whereas unpressurized gating system, you choke in the down screw. The advantage of choking in the down screw is the slag and dross builds up in the down screw, and then it does not go further down, even in the initial metal. In the case of pressure system, the initial metal takes in a lot of dross and slag, and your other aspects of the gating system, like the runner or the filter, should take care of the dross and gas and then prevent it from getting in the mold cavity. Now, this is not so unprocessed system. So I used to apply unprocessed system for, let us say, dross forming alloys like aluminum, stainless steels, where the chromium oxide can become a problem in 18-8 stainless steel and all that. I used to adopt it. But then there are a lot of very good and experienced foundrymen who differ with my view and watch on precise system for all or unprecise system for all. We can have debates. As I said, when the subject is not very well understood at the deepest levels, you can have anybody discuss, right? Ceramic filters in gating design is another aspect. Now, before that, people have vertical gating system as you have in disomatic, okay? Like bottom gating you have here, and there you have entry from the sides also. Okay. You notice one aspect here. They're all taken from ASM. You see here, this is smaller than this because it's really not necessary. There's only one gate coming. Okay. Right. Filters. Ceramic filters in gating design. There's a lot of debate whether extruded filters and foam filters are better, which is better than the other. You can discuss endlessly on both. And I have used both, and I'll be very happy, and I will consider a foundryman very lucky if he doesn't have a requirement of either. You can pour casting without a filter, you're lucky, because we don't really understand how it works. There are certain graphs here: flow rate, time, initial surge, normal flow, onset of filter blockage. What happens if applicable? There are distinctly two different schools of thought. One says that it should allow a lot of liquid metal. Another say it should not allow a lot of liquid metal. I think the ideal thing is it should allow a lot of liquid metal, but it should not allow dross. Now, how can that happen? It's anybody's guess. One thing which I've seen, the extruded filter, I think we have one example here. The third one, the middle one, the extruded. The last one and the other are, no, center one is the foam filter. The others are extruded filters. So this is what we use in Foundry. Now, you may use this filter, this in simulation study, what you are doing about it, and then it can tell you what is the type of defect you expect on this type of situation. So it's the mass flow.
I'm really happy with this lecture. And
Thank you very much.
Very thanks to you, doctor, and look forward to hear from you for the next session.